Good evening. Please tell your friend to join. Today I am going to discuss correlation index and correlation ratio. Yes, Shashwata, good evening. Mukho Prabhu, good evening. Swarnambu, good evening. Okay. So first I discuss correlation index. Yes, Pritam, we know we only use correlation coefficient when there are x and y are linearly related. Otherwise, for nonlinear relationship, we cannot use correlation coefficient. But this R square, which is called coefficient of determination, okay, Shashwata, now is it okay? Please tell me. Hello. Now is it okay? Please tell me, Shashwata. Okay, thank you. R square equal to coefficient of determination, which is nothing but a variance of, yes, Srijan, good evening. Variance of y hat by variance of y, where y hat is a predicted value of y, and we interpret this coefficient of determination as the proportion of the total variability of y which is accounted for by its linear regression on x. Now with this concept can be generalized. Yes, Shaya, good evening. Suppose the appropriate regression equation is polynomial of degree p, and this p should be less than equal to small n minus 1, where n is a total number of observation. Why? If number of unknown should be less than number of observation, otherwise we cannot estimate unknown coefficient, because for pth degree polynomial there are p plus 1 unknown equation. Since there are, for pth degree polynomial there are p plus 1 unknown equation, and n is a total number of observation, that means it should be less than equal to n, hence p should be less than equal to n minus 1. Okay, and the model is yp equal to a naught plus a1 x plus a2 x squared ap x to the power p. This is a pth degree. This is a pth degree polynomial regression equation corresponding sorry, it should be x to the power p. Please rectify this thing. So this is a pth degree polynomial regression equation corresponding okay, this is enough. This is a pth degree polynomial regression equation, and where a naught, a1, a2, ap are unknown. So we have in pair observation, that means we have xi, yi, I from 1 to n. So this means there are in pair observations. Hence, for x is equal to xi, this is written as ypi, capital Ypi, a naught, a1 x1 I, a2 sorry, this is a1 xi, a2 xi square plus ap xi to the power p, and I from 1 to n. So we can use yp or YPI is a predictor of small uh, small yi, or small yi which is the observed value can be estimated by capital YPI provided A0, A1, A2, AP should be known. But here this is unknown, so we need to estimate A0, A1, A2, AP by minimizing error sum of square. That means this is the observed value, ith observed value, which is denoted by small yi, and this is the predicted value of ith observations, which is denoted by capital YPI, whole square I from 1 to n. So this is the error sum of square. We already knew this thing in my previous class, and this can be written as sum over I from 1 to n small yi minus a0 a1 xi minus a2 xi square minus ap xip whole square with respect to yes, I'm telling this thing. Yes, Shashwati, you are right. This is called least square technique. Minimizing error sum square with respect to a1, a2, ap. This is which is called method of least square. Okay, and suppose I denote this by delta. Now partial derivative d delta with respect to a naught, this is equal to 0, gives first equation of the first normal equation, that is sum over I from 1 to n yi minus a naught a1 xi a2 xi square minus ap xip minus 2. So this is equal to 0. So this is equal to 0. So this implies summation yi equal to n a naught plus a1 sum over xi plus a2 sum over xi square plus ap sum over xi whole to the power p. Similarly, partial derivative with respect to a1 is 0 imply summation I from 1 to n minus 2 into summation I from 1 to n yi minus a naught a1 xi minus a2 xi square minus ap xip equal to 0 into into x1 into xi equal to 0. So this gives second normal equation. So yi sum over xi plus a1 sum over xi square, a2 sum over xi cube plus ap sum over xip plus 1 equal to 0. So similarly we can get the last normal equation as minus 2 into sum over I from 1 to n yi minus a naught a1 xi a2 xi square minus ap xip into xip. This gives sum over, sorry, this, there is a mistake, please rectify this thing. This should be summation xi yi. Okay, thank you. Please rectify this thing. This is my mistake. I rectify this thing. Please change this thing accordingly. So summation summation xi p yi, which is equal to a naught summation xi p plus a1 summation xi p plus 1 a2 xi p plus 2 ap xi 2p. So therefore the normal equations are so this is the first normal equation. Yes, Shashwat. So this is the first normal equations. Summation yi I from 1 to n a naught a1 summation xi a2 summation xi square ap summation xi whole to the power p. And this is the second normal equation. Summation I from 1 to n xi yi a naught summation xi a1 summation xi square a2 summation xi cube ap summation xi to the power p plus 1. And this is equal to I from 1 to last normal equation I from 1 to n xi whole to the power p yi. This is equal to a naught summation xi to the power p plus a1 xi to the power p plus 1 a2 xi p plus 2 ap xi to the power 2. Okay. So now solving this normal equation, we can find estimate of a naught a1 a2 a1 a2 ap, and use this estimate we can easily predict yi using yp. Okay, so now this is the total sum of square summation yi y bar whole square I from 1 to n. So this can be written as summation I from 1 to n yi minus capital YPI plus capital YPI minus y bar whole square. So this equal to I from 1 to n yi minus ypi whole square plus ypi y bar whole square, and cross product term should be vanishes. Y is c. So the cross product term this is equal to yi minus ypi ypi minus y bar. Now if you look at the first normal equation, you see that this is equal to summation I from 1 to n yi n into, I can write the first normal equation this as summation ypi. Why? Because ypi is nothing but a naught a1 xi a2 xi square ap xi p. So if you adding all ypi, capital ypi, then you get n a naught a1 summation xi plus a2 summation xi square plus ap summation xi whole to the power t. So this is the normal equation 1 does implies summation small yi is equal to summation capital ypi. So therefore this imply y bar equal to capital yp bar. Okay, and hence this equal to summation I from 1 to p n yi capital ypi equal to capital ypi. Sorry, please change this notation. This should be capital ypi. So this should be capital ypi. Okay, so capital ypi. So why this thing is happened? Because you see that this can be written as this yi minus capital ypi, and in that summation yi minus capital Pi is nothing but a summation yi minus summation capital Ypi. So this should be 0. So this part is same as summation I from 1 to n small yi minus capital Ypi into Ypi. Now consider this term summation yi minus capital Ypi into capital Ypi. Okay, and this is, if you look at the all normal equations, then you see that first normal equations, please listen carefully. This first normal equation gives summation small yi minus capital Ypi. Agree? This is equal to 0. And second normal equations gives you summation yi minus capital Ypi into xi. This is equal to 0. Similarly, third normal equations gives summation yi minus capital Ypi xi square equal to 0, and so on. And lastly, we get summation yi minus capital Ypi xi to the power p equal to 0. Okay, so please see that we can write the normal equations, or we convert this normal equation as. So if you add, now look at this thing. So this sum is nothing but a yi minus capital Ypi, and capital Ypi is nothing but a naught plus a1 xi plus a2 xi square plus dot 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 plus ap xip. So therefore this is yi minus ypi so this is a naught ypi a1 sum over yi ypi xi plus a2 sum over yi minus ypi xi square plus ap sum over yi minus capital Ypi xi to the power p. So if you see that, if I multiply these normal equations by a naught and then adding a to the second normal equation and multiplied with a2 with second normal equation and so on, we get this. And since all these parts are 0, we can write this equal to 0. Okay, so please tell me, have you any trouble? So therefore we can write this sum of I from 1 to n small yi minus capital Y bar whole square equal to sum over I from 1 to small yi minus capital Ypi plus sum over capital Ypi minus small y bar whole square. And moreover, we see that small y bar equal to capital Yp bar, so we replace small y bar by capital Yp bar. Whole square. So the sum of products, so please mention this thing, sum of product terms vanishes or vanishing by virtue of the above normal equation normal equations determining determining ypi and y bar equal to capital Yp bar. Okay, so now we can write this sum of I from 1 to n yi minus y bar whole square into 2 sum of square. One is I from 1 to p small yi capital Ypi whole square, and another is sum of Ypi minus capital Yp bar whole square. Now we see that this sum is nothing but a total sum of square or total variation, and these total variations explained by two parts. This part is sum of square due to polynomial regressions, and this part is sum of square due to errors. Why? If you look at the first sum, then you see that this is the sum of square due to the difference between yi minus capital Ypi. Yi minus capital Ypi is nothing but a error, and this error due due to this difference. Yi is a observed value, Ypi is a predicted value. This predicted value obtained using pth degree polynomial. So this is the unexplained part. So this is the unexplained part, unexplained part, unexplained part, and this is explained part, and this part is explained by regression pth degree polynomial regression equation. Okay, so total variations, this total variations break into total variations means the variation within the observations or response variable that is that this is nothing but a sum over I from 1 to n. This is nothing but a sum over I from 1 to n yi minus y bar whole square, and this can be divided into two parts, that is the unexplained part, the variation due to unexplained part, which is called sum of square due to error, and another part, this is the explained part, and this explained part is called sum of square due to periodical regressions. So now we can check that. Now our next task is we want to show that as the degree of the polynomial increases, the value of the correlation index also increases. So first I define what do you mean by correlation index. I already mentioned that coefficient of determination can be used as a measure of or strength of the regression equation. So, and this correlation index is not the correlation coefficient. Coefficient of determination is nothing but a ratio of the two variances. The variance of capital Y, that means variance of explained part, that is Y, capital Y is a predicted value. So this means this is the variation due to explained part, or this part is explained part, and this is the total variation. Okay, so instead of capital Y, if you use this is hold for, and we use this for linear regressions, that means capital Y equal to a plus bx. Now we assume that there is a pth degree polynomial, that means y is a pth degree polynomial, that means a naught plus a1 xi plus a naught a1x plus a2x square plus apx to the power p. So instead of y, we write this as yp, and instead of r, I write this is rp. So this is a correlation index of pth degree polynomial, and this is nothing but a, so variance of capital YP, that means explained part. So explained part is this sum over YPI minus YP bar whole square by, this is the total variation, small yi minus capital Y bar, yi minus small y bar whole square. Okay, so this is the correlation index, and yp is, y capital YPI is predicted value of small yi. Okay, so now come to the point, that is we want to prove that as degree of polynomial increases, the value of correlation index also increases. That means rp square is greater than rp square rp minus 1 square. That means rp minus 1 square means this is a, this is correlation index based on p minus 1 on a degree polynomial. When we use for prediction p minus 1 degree polynomial, then the correlation index is r square p minus 1. Okay, so let the polynomial regression equations of degree p and degree p minus 1b respectively and I use star for p minus 1 in degree polynomial. Okay, and for estimating constants we use least square technique. So we write this as the constants a naught ap and a naught star a1 star ap minus 1 star are determined by the least square method. Okay, so we know if you consider this for pth degree polynomial, least square method tells us, so by the definition of the least square method, we minimize the error sum of square. That means this is a observed value and this is predicted value, that is capital YIP, and one thing it is better to write, I forgot to mention this thing, capital Y in suffix p and capital Y in suffix p minus 1. So this means yp means I use pth degree polynomial, and yp minus 1 means I use p minus 1 in degree polynomial. Okay, so ap xip whole square. Now this should be less than equal to sum over yi minus a naught a1 xi minus a2 xi square minus ap minus 1 xi p minus 1 whole square, because this is this there is a less number of parameters when you use p minus 1 degree polynomial, and this sum of square for p minus 1 degree polynomial, this sum of square right hand side, this part should be greater than equal to this part, because here I use 8 degree polynomial. Okay, so can you justify how can I reach this thing? Because see, by definition of least square means what? If this sum of square, minimize this sum of square, okay? We minimize this sum of square. So this sum of square of suppose a naught a1 a2 ap, please listen carefully, okay? Please listen carefully. A naught a1 a2 ap, these are the least square estimators. If these are the least square estimators, then this is always true whatever whatever the alternative set, the alternative set of constant bi may be. Listen carefully. According to the least square method, we know we minimize error sum of square with respect to unknown constant, and that means if a naught, a1, a2, ap, these are the, please listen carefully, a naught, a1, a2, ap, these are the list, if these are the least square estimators, then this sum of squares should be minimum for any choice of b0, b1, bp. This is the principle of least square method. So now this is also true for if we choose b0 equal to a0 star, b1 equal to a1 star, bp minus 1 equal to ap minus 1 star, and bp equal to 0. So this implies so this implies this. Okay. So please tell me, have you any problem? So listen carefully. If a0, a1, a2, ap, these are the least square estimators, this means this sum of square left hand side part should be less than equal to sum of square of right hand side part, where b0, b1, b2, bp, any choice, alternative choice. This is called the least square principle, because according to the least square principle, it minimizes sum of squares. Okay, the solutions minimizes the sum of squares. So therefore, if we choose b0, b1, bp minus 1 and bp as follows, so this choice is different from a0, a1, a2, ap. This implies the left hand side should be less than equal to right hand side. Okay, so please tell me if you have a still doubt. Okay, please tell me if you have any doubt, still have any doubt. So from this implies you can write small yi minus, this part is minus of capital YPI whole square, I from 1 to n, and this is less than equal to sum over I from 1 to n small yi, and this part is minus capital YP minus 1i whole square. So therefore if you divide both sides by same quantity, then inequality is unchanged. Therefore, I divide both sides by sum over I from 1 to n yi minus y bar. Before doing that, one okay, no problem. So this is I from 1 to n sum over yi minus y bar whole square sum over I from 1 to n yi minus capital YPI whole square less than equal to sum over I from 1 to n small yi minus capital YP minus 1 I whole square divided by I from 1 to n yi minus y bar whole square. I divide both sides by same quantity, that is I from 1 to n yi minus y bar whole square, hence the inequality is unchanged. Now I consider this part. I already proved this thing. So this part, we break total variation into two parts, that is the unexplained part and this is explained part. So therefore, we write this as summation yi minus ypi whole square equal to summation I from 1 to n small yi minus y bar whole square minus sum over I from 1 to n capital YPI minus YP bar whole square. Or if you divide both sides by summation yi minus y bar whole square, so this equal to summation yi minus capital YPI whole square divided by total variation yi minus y bar whole square, this equal to 1 minus rp square, because rp square defined as follow. Okay, so similarly, so this part is 1 minus rp square. Okay, similarly the right hand side also we can write this as 1 minus rp minus 1 whole square. So this implies rp square greater than equal to rp minus 1 whole square. So this means if you increase the degree of polynomial, this means your value of correlation index also increases. That means you explain more of yi if you increase the degree of polynomial. Okay, so taking p equal to 2, 3, n minus 1 respectively, successively, it is better to write successively, we thus have r square means r1 square. R1 square means this is simply the way we consider the linear. First degree means linear, that is y equal to a plus bx. So instead of r1 square, I write r square. So I better to write this thing in that way. R square equal to r1 square less than equal to r square, r2 square. This is a second degree polynomial. This is a third degree polynomial, and so on. Okay. Now I consider correlation index. Okay, so please wait. Sorry. Okay, fine. So please tell me if you have any doubt. Okay. Now we consider correlation ratio. Now we shall consider introduce. I think it is better to write introduce a more general measure of the degree of dependence of one variable on other. To suppose the n pairs of values of x and y are arranged in arrays of y according to fixed values of x. That means for x1 there is n1 y values, for x2 there is n2 y values, for xk there is yk nk y values. So this means that for ni of the n individuals, the values of x are the same, namely xi, while the values of y are yi1, yi2, yi ni. Define yi bar, this is called array mean, by ni, and so this is called the mean of the ith array and y bar, which is called grand mean, this is equal to I from 1 to k ni yi bar by n. This is called grand mean of y, and when n equal to sum of ni I from 1 to k. This is called total observations. And x bar which is equal to sum of I from 1 to k ni xi by n, because x1 actually, if you consider the pairs, that means x1 appear in 1 times in this pair, x2 appears in n2 times in this pair, xk appears nk times. So if you consider the pairs, so this means this pairs, okay. So x bar is nothing but I from 1 to n xi by n, not sum over I from 1 to k xi by n, xi by k, because x1 actually pairing all these n1 y's, x2 pairings all these y n2, and so on. So for x1 actually there are x1 appears n1 times in pair, x2 appear n2 times in pairs, okay, and so on. So this means x bar is nothing but a sum over I from 1 to k ni xi by n. So please think carefully. This x bar is not a sum over I from k xi by k. It should be sum over I from 1 to k ni xi by n, because x1 pairs with yi's with n1 times, because this consider x1 y11 x1 y12 dot 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 x1 y1 n1, similarly x2, similarly x3. So if you look at this data set, then you see that basically x1 appears n1 times, x2 appears n2 times, and xk appears nk times. So this means as a whole x bar should be sum over I from 1 to k ni xi by n. So now if the regression of y on x were linear, a measure of the dependence of y on x or the or of the interdependence of x and y would be modular given by this is the correlation coefficient. So just that's why I'm telling you this should be impaired. Okay, so just arrange this data in that way. X to y to 1, y to n2, xk y1 y sorry yk 1 xk yk2 xk yk nk. Okay, so now compute the correlation coefficient. So this means I from 1 to k sum over j from 1 to ni xi minus x bar yi j minus y bar by root over summation I from 1 to k sum over j from 1 to ni xi minus x bar whole square sum over I from 1 to k j from 1 to ni yij minus y bar whole square. Okay, so this is equal to sum over I from 1 to k ni xi minus x bar yi bar minus y bar divided by sum over I from 1 to k ni xi minus x bar whole square into sum over I from 1 to k sum over j from 1 to ni yij minus y bar whole square and r square, which is a variance of capital Y, that means summation I from 1 to k sum over j from 1 to ni capital yi minus y bar whole square, because we know mean of the predicted value is same as mean of the observations divided by total number of variations yij minus y bar whole square, and this is simply written as sum over I from 1 to k ni yi minus y bar whole square sum over I from 1 to k, j from 1 to ni, yij minus y bar whole square, where capital Yi is the value of small y corresponding to xi as given by the regression line is wait. Okay, all right. The regression line capital Yi equal to a plus bxi, and where a and b are obtained by minimizing, this is the least square technique, sum over I from 1 to k, sum over j from 1 to ni, yij minus a minus b xi whole square with respect to a and b, or this is because, see that if you look at these equations, then you can write this as not necessary, you can with respect to AB. Then the normal equations are ni yi bar sum over I from 1 to k equal to n into a plus b sum over I from 1 to k ni xi, and this is equation number 1. And equation number 2, this should be sum over I from 1 to k, that is partial derivative with respect to b, is obtained by partial derivative with respect to partial derivative of delta with respect to b, and then equate it to 0, then you get sum over I from 1 to k ni xi yi bar minus a sum over I from 1 to k ni xi plus b sum over I from 1 to k ni xi square. Okay, I denote this by equation number 2. So now you can erase this part first. Fine. Now it would be apparent from okay, this is not required. I think it is better to write in that way. The expression, I denote this expression by capital A. So the expression capital A also shows that mod R, or absolute value of R, really purports to be a measure of the extent to which the array mean of y for given x depends on x. In case the regression is linear, that is, in case yi equal to small yi bar for each I, mod R, or absolute value of R, achieves this purpose. But as we have already stated in our case, the regression is not linear, and Alternative measure is called for the, so we need to modify mod r through the replacement of capital YI bar in, I denote this by B, in B by small y bar. I think it is not capital Y bar, it is capital YI in B by small y bar. The new measure obtained called the correlation ratio of y on x and denoted by EYX is thus the positive square root of EYX square sum over I from 1 to k ni. Just think about this. Small yi is, capital YI is replaced by small y bar minus small y bar whole square divided by total variation, this part. Sum over I from 1 to k, j from 1 to ni, yij minus y bar whole square. So the root of these values is correlation ratio. Okay. So for group data, for group data, so for group data, that is k cross L bivariate frequency table, the k classes of x may be supposed to give k arrays of y values for ith array the total frequency is fi naught and the array mean is small y bar, which is equal to sum over I from 1 to k fi naught into so it is better to write in that way yi bar, so this is equal to sum over fij yj yij divided by fi naught sum over j and grand mean equal to y bar, which is equal to summation fi naught or it is better to write double summation fij y, oh sorry, there is a mistake, it should be because yi appear, please change this thing because this is a k cross l bivariate frequency table and kx values and y value k arrays of y values, so it should be yj because yj appear if fij times, okay, so yj appears fij times, it should be summation j fij into yj by fi naught, so therefore y bar, this should be fij fij yj by small n is a total frequency and here we see that yj sum over I fij by n, which is equal to sum over f naught j yj j divided by small n, so this is equal to the grand p, so therefore in that situation the correlation ratio is the square root positive square root of exy whole square, which is equal to, because here instead of ni it should be fi naught into I bar minus y bar whole square divided by total variation, that should be f naught j yj minus y bar whole square. Okay, and note that summation, double summation ij yij minus y bar whole square k into ni, sorry, sum over I from 1 to k and j from 1 to k ni yij minus y bar whole square, this part can be written as, this can be break into two part, yij minus yi bar plus yi bar minus y bar whole square, and since the cross product term vanishes, just we can write this as since cross product term that is equal to I from 1 to k, j from 1 to 9, yij minus yi bar, yi bar minus y bar. So this can be written as I from 1 to k, yi bar minus y bar into ni into yi bar minus y bar, yi bar. So cross product term is vanishes. And this equal to s square total variation, okay, and this part within variation, and we write, if you look at this formula, then we see that first I write this part, second part, if you look at the formula, then you see that this is nothing but a e square yx s square, which is equal to sum over I from 1 to k a9 yi bar minus y bar whole square. So second part is e square yx s square, and the first part should be, because this is due to the addition, so first part should be s square minus e square yx s square. So it is simply as please wait. So here it is. So this is equal to So this is equal to 1 minus e square yx s square plus e square yx s square. So now you see that ni yi bar minus y bar whole square, this can be written as ni yi bar minus capital Yi plus capital Yi minus small y bar, and again we see that the cross product term vanishes. Please check this thing. So we write this as a product of two sum of square. Okay, I already show this thing uh, in correlation index portion, because if you use the all normal equation, then you can easily find that the cross product term should be vanishes. So please verify yourself. So therefore, or from this, one minus e square yx which is equal to sum over I from this part, sum over I from 1 to k, j from 1 to ni, yij minus yi bar whole square into s square. So this should be greater than equal to 0. So this implies e square yx should be less than equal to 1. This is the upper boundary of correlation ratio. Okay, again now consider this portion. This is come from here. Okay, this is come from here. So now consider this portion. Okay, so now if you dividing both sides by small n, we may write, say this part is nothing but a look at this portion. So this part is nothing but a e square, because this is e square yx s square. Okay, so this part is nothing but e square yx s square, and this part, so just see the part I already mentioned this thing. Either erase this part or okay, no problem. Just I think I erased this part. Okay, so please check yourself and check the note, please. Okay, so r square, I define this term r square, which is equal to sum over I ni capital Yi minus y bar. I think I denote this equation number A. Please check equation number capital E. Okay, I denote this by capital E. So this is equal to sum over I, sum over j, yij minus y bar whole square. Okay, so you see that, so these portions from A, this is equation number A, this is equal to sum over I ni yi capital Yi y bar whole square. This is equal to r square into s square, because this is a s square. This is the s square. So this should be right as is r square s square, and we see that this is e square s square is a sum of two parts, and one part is r square s square, then sum over ni y bar y capital Yi whole square. Please listen carefully. Sum over ni small y bar minus capital Yi whole square is nothing but a e square yx s square minus r square s square. So this is equal to e square yx minus r square s square plus r square s square. So therefore e square yx minus r square is nothing but a 1 by s square. This part sum over I ni small y bar minus capital Yi whole square. So this is sum of square. If you look at the right hand side of e square yx minus r square, this is a sum of square, so it is always positive, so it is greater than equal to 0. This means e square yx greater than equal to r square. We already get this thing, e square yx less than equal to 1. Now we get e square yx less than greater than equal to r square. So combining C and D, we see that r square less than equal to e square yx less than equal to 1. Okay, so and now we see that if e square yx equal to r square, so this equal to means, this means the sum of square should be equal to 0. The sum of square should be equal to 0 means, so this occur if and only if sum of square should be 0 means individual term should be 0. So this means if and only if capital Yi should be equal to small yi bar for each I. So array mean of y is same as capital Yi. That is the predicted value of small yi, small yij for each I. Hence, the difference E square yx minus r square measures the extent to which the true regression of y on x, that is the true relationship between the array mean of y for given x and x departs from linearity, departs from linearity. So from this we can conclude that the correlation ratio serves as the least upper bound to the numerical value of the correlation coefficient. Or correlation index. Why? Because instead of linear you can use phase degree polynomial, then again you see that e square yx greater than equal to. So instead of using linear you can use, if you use phase degree polynomial, then you can easily, using same procedure, you can easily show that e square yx greater than equal to rp square. So this is your homework. Please verify all these steps, okay, and prove that e square yx greater than equal to rp square. So as a result, we can write this e square yx, this is greater than equal to, less than equal to 1, this is greater than equal to rp square, and then p minus 1 square, and so on, and lastly r square, and this should be greater than 0. Okay, so this means is yx greater than rp absolute value. So this is the rp. I think it is better to write absolute value. Okay. And lastly, greater than 0. Okay. So the last point, just as r square may be interpreted as the proportion of the total variation of y that is explained by its linear regression on x square yx may be interpreted because consider this part. I already mentioned this thing. So this part s square can be written as, just see this part, because s square can be written as 1 minus s square yx. This is the unexplained part. I repeatedly told this thing. E square y s square, this is the explained part, and this is the unexplained part. Okay, unexplained. So because the total variation can be split into two parts, the explained and unexplained part, as the proportion that is explained by the array means of y for given x values. Note that correlation ratio is not symmetry. That is, eyx and exy may not be equal, but we already observed that correlation coefficient is symmetry. That is rxy equal to ryx. The last point, what happened if square yx equal to 1? So square yx is equal to 1 means, if you look at the part is this. So that means this should be 0. Summation I from 1 to k, j from 1 to ni, yij minus yi bar whole square equal to 0. This means individual terms also 0. So all yij is same as, and same, it's array mean. That is, for ith array, all observation of ith array is same, and that is equal to their mean, that is yi bar. Okay, so please tell me, have you any problem and doubt? Please tell me if you have any queries. So these are all about today class. So please tell me if you have any queries and doubt, and we will meet again on Friday with new topic. Okay, thank you, Sharnavo. Good night, everybody. Okay, so we'll meet again on Friday, same time with new topic. Okay, thank you, thank you, thank you, Alko Prabhu.